Okay, welcome back from lunch. We're going to get started with the first breakout session. And again, the purpose of this breakout session is to talk about mission concepts. And what we hope to do today is to walk away with some mission concepts, presumably after those in the science community have had a chance to talk with those in the autonomy community, and maybe the ideas are a bit more refined. What we intend to do going forward is to, between now and the next workshop, which tentatively we're scheduling for Pittsburgh sometime in the late spring, although that could change, is to put out an RFI based on some of the ideas that we come up with today. I have been told that at least one of the divisions of SMD is willing to put funding on some studies. So there will be an opportunity I'm now being told 2 divisions are willing to put money on studies. So there will be opportunity to do some real work and actually get paid for it. And ultimately, after the next workshop, we would like to be able to determine if we need a new program to accommodate some of these ideas going forward. So this meeting today is really a pathfinder to determine where we go next. So with that, I think we're ready to hear from some of our breakout groups. And Butler, I think you had volunteered to go first.
I think Terry volunteered.
Okay, you were volunteered to go first. You can use the cube, but you might want to use this.
So good, at least one team member is here. Okay, so we were a merger of group 18, 17, and some stray. So, but we had 6 people. So the mission we targeted was the Mercury Pole mission because we had Ariel in our group. The science goal of that mission is ice composition and extent in the permanently shattered regions. So that's the science driver. And then the mission implementation would be core sampling the ice in multiple locations, and then determining the composition from the core sample with depth, and then also getting the samples or coverage over a larger area to disambiguate some of the models for the ice transport into these regions. So to do that, you've got to go core sampling in multiple locations. You've got to cross crater boundaries, which implies difficult terrain. So the ice within the PSR kind of is the ice rink model where it's terrain variances of meter or less, but then going between the ice rinks involves very difficult terrain, especially between the craters. And there's an aspect of this mission where you do not have line of sight communication to the Earth. Once you're in the shadowed region, you have no communication capability. So you have to solve that with some other mechanism, either an orbiter relay or relay through an asset that's up on a crater wall or moving in and out of the crater. So we made a couple of assumptions based on this class of mission. One assumption is that landing in a safe spot is doable from Mars technology. So the sky crane approach does not contaminate the landing site, and then we're assuming that the onboard navigation can take you to a relatively flat spot that's safe to land. So we made that assumption that that was a solved problem. The other assumption we made is that nuclear would not be available, nuclear power would not be available for this class of mission, so we're assuming it's solar plus batteries rather than nuclear. So once you take all of that, the autonomy challenges that result from this are first getting data back to the Earth. So you can either go with a more complex mission, which has an orbiter relay, comm relay, which is actually a challenge around Mercury. You can have the complexity of a comm relay where it's a second lander that sits up on the rim and relays comm, or you can have mobility in and out of the shadow. So you do your sampling in the shadowed region, and then you go out of the region in order to do COM. Because you can only do the science sampling within the shadowed region, which is not in contact with the Earth, it means fault recovery cannot be passive. You can't do the stop and wait for an instruction if you run into a fault. Fault recovery has to be active rather than passive, because you actively have to recover your capability to either move out of the crater or in order to establish COM. The third aspect is the mobility in the inter-crater terrain. It's a very challenging terrain, so how you do mobility is a challenge. It's given the distances involved for the mapping, you're probably not going to be able to do this with wheeled rovers. The approach that we were drawn to is a hopper approach, where you hop around to take the core samples, but you also hop to get in and out of the crater, and then hop for the distances you need for the mapping. We looked at and discarded that science decision-making was not required. The type of measurement that you're making does not require you to assess the sample and then change your plan. So that's often a strong driver for autonomy. In this mission, it was not a driver. But because of the assumption that we're not going with nuclear, power management is difficult. It means you have to actively manage your power state much more rigorous than you often have to. So example is you have to manage your power to do the measurement in the PSR, but then you have to move out to get to a place not only where you can communicate with the Earth, but also where you can recharge your batteries. And then you have to move back into a region where you have no COM and you're in a power negative situation. So power management in this case could benefit from autonomy quite a bit. So given this mission, we came out with 5 strong drivers and 1 not a driver. So, that's it.
Okay.
If anybody has a slide that they would like to show when they're briefing, please raise your hand and I'll come by with this USB key. Anybody? So Sangdar's group was the overachievers. All right, thanks.
Good, thanks. Okay, so which group would like to go next? Volunteers? All right, Jeremy.
All right, so I'm going to go stand over here by our chart. I want to go next because we're slightly duplicative with what Butler just talked about. We also were interested in the Mercury mission concept, and we were also interested in the Europa mission concept. And so our group, which was also sort of a scratch team, talked a lot about one aspect of such a mission that we thought was most compelling and interesting, which is the idea of a fully autonomous robot arm or set of arms. And the idea is that this arm or arms might have a number of end effectors on it in order to do basically sample manipulation, not necessarily a drill or drilling, but combinations of cameras, probes, maybe scoops in order to move samples and other things like that. And the piece of the puzzle that we thought was interesting was, if you look at the way that classic arm ops are done today, we're closing the loop on the ground, and for these further destinations and fully autonomous missions, that's going to reduce the amount of science that you have. So, can you have a fully autonomous robot arm? And by fully autonomous, we meant a lot of different things. We meant the ability not only to plan its own motion, but to choose its targets, possibly to characterize itself, either for nominal operations or for fault cases, and also select targets, analyze samples in situ, basically to do everything that the ground team is doing, but to do it on board. And so what are the benefits? More science, better science, adaptive science, fail operational, autonomous replanning, and all sorts of other things like that. We had a little fun with the idea, and we conceived of the idea of a system with many arms, the Octobot, and we speculated on what that might mean. If you mount your arms on the very edge of your spacecraft, maybe you get a slight increase in the sample area, maybe you don't. You also now make the range of motion required for each arm a little bit smaller. Maybe that trades mass for simplicity, maybe it doesn't. Obviously, someone would need to do a mass trade on that. So that was kind of fun, but possibly not terribly realistic. We talked a lot about some of the challenges in a system like that, and I won't go through them, but it's the usual thing. Among them, I think the most interesting is that the state of your robot arm is the hardest to know and understand. If there's any kind of flexibility in the structure, or if the structure is degraded over time, a lack of precision in the position of the joints or the end effector is possibly the most unsafe thing about a fully autonomous arm. So in order to deal with that, maybe you need more sensors and you need more complex processing of those sensors. The sensors themselves can be inherently failure prone. That increases operational complexity, which is bad because that's the whole thing that you want to get away from. And then we had a list of sort of interesting technical opportunities that one might pursue, things like soft robots, tensegrity robots, smart matter embedded with many, many different sensors that give you much more precise information about the state of your arm, all the way down to things like variable end effectors. So I think this is a nice complement to what Butler just said, drilling down into one single system.
Thanks very much. Any thoughts, comments? Octobot? Okay. All right. Mm-hmm.
I wonder if you could actively, if the arm degrades, if you could actively learn that it has degraded, and so it relearns how to move and to be precise again based its current state.
Okay. All right. Who's the next victim? All right. Thank you.
These are my slides here. So we were started off as all technologists, and so we got some science help at the very end, and we tried to incorporate a little bit into our mission. Our other, I guess, handicapped, a couple of us actually work at AMD, where there's a lot of autonomy, but we don't understand on the space side. Probably a plug for that. That's probably an area where there's more cooperation, when we look at UAVs and swarming and things like that. So it's a lot of common problems, different missions. So our concept, we kind of looked at, didn't pick anything there, but looked at lava tube exploration, both for an automated rover type thing, but also as a teleoperation with future astronauts. And the reason the reason for autonomy we feel is it's difficult to perform this from ground control. You may not have all the insights. You may have danger lurking. You have a time constraint. You can't spend a long time making decisions. Astronaut risk reduction, obviously you don't want to send astronauts in. You want something to explore ahead of time. So that's kind of a challenge why we think autonomy would help this. Possibly more efficient exploration. So, looking at the lava tubes areas maybe an astronaut can't get to, more mapping and things like that. One of the concepts we had is rover decision-making. So can we program the rover to make decisions? And again, to risk, if there's some good science, but the risk of losing the rover, can we program the rover to look at that? Or possibly, as we were looking at this mother-daughter rover, where we have a main rover with smaller ones that are basically sacrificial. So if there's something of interest that may be risk but is time critical, they could look at that. So we look at the risk. Of course, loss of the rover with the multiple rovers, you have more complexity, but you can make that risk decision. The biggest thing, of course, is risk of mission. That something we're doing is going to affect the overall mission. I think that's a big concern and why it's difficult to get autonomy in some of these exploration missions. One of the biggest autonomy is goal confusion. So if you're having it make decisions, how do you know what it's doing? That's always seems the question we find on the aircraft side. What's the autonomy doing? So how do you communicate that to operators, astronauts, or so at least you understand what the thing is doing? One of the other things we notice is state of the art. So you look at the growth of autonomy and how fast autonomy is moving. you have breakthroughs, weekly and monthly, stuff is progressing. But generally on the mission, you picked your hardware and software, years before the mission. So you may have lost some of the advantage of implementing some of that technology that would possibly help the mission and such. And we kind of ran out of time, but risk reduction. So somebody had mentioned, simulation. How do you simulate this? How do you find Earth equivalents? So, can we let's look at lava tubes and lunar, possibly lunar tubes and stuff like that as initial for going to Mars. Other simulations, and again, kind of broader. One of the things we looked at was remote, looking outside. So robotic submersibles, that they're using now currently. That's a very rough environment, for looking, how can we use that for, say, testing technologies. So that's what we have. We'll talk to scientists a little bit more, but I think we got a good start.
Okay, comments? Any other thoughts? Okay. Yeah, comment?
So when you're inside a tube, obviously it's dark in there. How are you going to tell where you are? You have some options. The thing that I find most interesting about that is, I do planning, scheduling, and fault management, but vision processing is one of those exceedingly computationally intensive things. So I'm not going to have solar power from my vehicle inside my tubes. So I had this very interesting combination of problems. It's sort of the spacecraft problem writ large. I have thermal management, compute, and battery. So did you think about that?
I should have come to my I can't catch, so that's another job. So we did think of that. We focused a little bit on the mission itself and using that, but probably the real value is doing that is as much autonomy we can do it for monitoring that. So kind of another example we thought of, on the solar. Again, this. Do we use all our solar, if we find something interesting, can we use all of our energy reserves to go pursue that, versus, we're going to stop and rest reduction. But yeah, just managing that, I need to charge my batteries. Initially, we looked at technology. I know some folks looked at computers, and I kind of look at it, at the UAV, and you look at current UAVs can do quite a bit, even with very simple processors, but like the vision, and when you get into that, it's much more complex and such. So we do see the need for that. We were looking a little bit more for mission, but yeah, for the general systems, health monitoring and stuff, I think that's a real, for any of this, that's where the autonomy is really going to pay off.
Okay, other comments? Thoughts on the mission concept?
So on the MSL mission, they had something like of the order of 10 test tubes with, to use for wet chemical laboratory testing of the drill samples. To date, they didn't use any of them, and now the drill is broken. So I'm thinking in your concept of the sacrificial items, whether you'd be so reluctant to actually use them, to save them for later, that they'd never get used.
Yeah. It's a good, and we pointed that, sometimes it can be, we look at the case where it may have to be immediate decision. Obviously, we want ground controller in an astronaut. You probably want them making that decision, but in some cases, can you give the autonomy to say, hey, I'm going to sacrifice myself because I think our example was there's a Martian running across, do we go explore that or do we save our batteries? And, so we'll take the risk of losing it because we see an opportunity. The programming that's difficult because you've got to provide something on your objectives and missions and what you're thinking. Because in the end, somebody's going to say, why did you guys program that? And something when you do is it.
Okay.
We actually have a few charts.
Okay.
Ricky, can you put the first chart up? So whose group is this?
That's me. Thank you very much. Okay, so I happen to be working on the Europa lander project, so this is a little unfair, right? Okay, but in the same context, all that really means is whatever great ideas you get from me will show up actually in the project. So come on, give me good ideas. But like some of the other folks have mentioned, right, this is a very constrained mission in a whole bunch of different ways, mostly based on what we've done to ourselves to some degree, right? It's very power constrained, right? So it has a very limited lifetime. It's in a radiation environment where its lifetime is slipping away, right? It's a combination of both a lander and a relay spacecraft, where the relay spacecraft has similar lifetime issues, right? It is sitting in a radiation environment where it's just getting pounded. And on top of that, it's driven by the concept that the science wants to be part of the decision-making about what has to happen. And it's a sampling mission, right? So you need for the scientists to have the opportunity to select where to sample, look at the results of the analysis of that sample, and repeat that multiple times within this lifetime, okay? And if you look at the lifetime as a function of days, right, and you imagine a 20-day lifetime, you say, hey, I don't want to waste any more than like 1% of the time, right? 1% turns out to be 5 hours, right? So you think about the combinations of the power, the combinations of the ability to do things quickly and successfully, the environment we're in where you might be getting constantly or frequently interrupted, so you cannot stop and wait for the ground to come in and intervene. On top of that, you're tied to a communication path that is many hours long in terms of both the light time, the work that are done by the ground team, and then the response back, and the fact that you have to go through a relay orbiter in both cases, okay? So communication now is a critical thing, so you can't wait on either side, either the relay or the lander, for communication issues to be resolved by the ground. So, of course, the goal here is how do you maximize the science return? So in that same context, with this limited power, you want to be transmitting that last bit of the most recent part of the investigation data coming out of the instrument that you just got from the most recent sample when you can no longer have enough power to fetch your last instruction in your computer, right? So you want to carry this all the way through the end. So, and then on top of all that is the challenge that we're in an in-situ environment that we don't understand, okay? So we want to build a sampling system, for example, that given our constraint that the scientists will want to pick where to sample, from that point on, we want it to be as autonomous or at least as automated as it possibly can be, including potentially the fact that things like fail to progress or the amount of sample was insufficient. We want to be able to not only sense those things, but then have points where we can make decisions about what to do. For example, if we are given a site where the hardness of the material is such that we're not obtaining enough sample fast enough, maybe the choice now is to abandon that and use the energy that we have, that we've allocated for this cycle, at a different site. And so just thinking about the sensing you would have to do to be able to do those things, I think is the linchpin of a decision capability that we would have to have on the vehicle. The other thing is if for some reason the vehicle condition deteriorates for reasons that I won't speculate, but let's imagine it's an energy storage problem. If all of a sudden your rate of energy consumption changes, do you want to proactively accelerate the activities that you're doing? Do you want to now autonomously gather samples that you might have left for the ground to select their locations for later, but do you still want that capability on board to do it just in case you end up with a fault or a failure scenario that might be driving that? And we have to make the assumption at this point in time, just given the uncertainty of the environment at Europa, that we may get interrupted. The system itself should never fail safe in the parlance, right? But actually pick up where it is, what it was doing, and continue those activities. And that requires an infrastructure of knowing where you were and what you were doing. It also requires things like an infrastructure to reestablish state of like your sampling system, right? Your arm, your mechanisms, right? You would have to have the ability to know where you were and continue, or at least basically roll back and begin again in some aspects. So I would say our solution didn't get very far here, but I would say that many of these things will require us to capitalize on the types of capabilities we've put into the rovers on Mars. But that's not sufficient, right? And so what we're going to need is a set of sampling capabilities related to the direct science that we're taking, particularly the sampling. And we're going to have to come up with strategies which are within the realm of fault tolerance that we do now that allow us to continue operations, reacquire communications, possibly by either detecting communications issues or just using multiple configurations. And we're probably going to have some functional redundancy here too. A single sampling mechanism may not be the right approach. Maybe we need a primary sampling mechanism and a backup way to do something similar. Anyway, that's my summary.
Is there another? Okay. I would ask questions, but we're running a little short on time. So. They have to do it? Okay. Do we have a group that does not have slides? Okay.
Okay, we're group 2. The mission that we looked at was the Venus mid-atmosphere atmospheric sampling using balloons, airplanes, airships, probably a wide variety of different kinds of sensor platforms. The basic assumption behind this mission is that we have at least one orbiter. We have a series of these platforms that will be able to relay via the orbiter. And applying autonomy, we have to have it to do the mission. So this is, if you will, a strong form need for autonomy. We're not trying to trim time off or trying to get the price down. We're actually trying to accomplish the mission and can't do it without it. So in this particular case, we need the autonomy for platform coordination in order to gather together and make decisions in a large form process for looking at chemical traces and other detections in order to make decisions regarding our altitude dwell profile and replanning. So the basic form that this would take would be to deliver these various platforms into the atmosphere and coordinate their position in the atmosphere together so that we can detect atmospheric layering and atmospheric dynamics inside Venus's mid-atmosphere. That requires that sensed information be coordinated and transmitted between the platforms, and that this chemical detection feedback affect the altitude profile. The mission length is measured in months or possibly years, so this is something that is put in fundamentally and enables the entire mission to gather the new science. One way of looking at this is that we need an intelligent and robust controller in order, in the GNC process, in order for the guidance and navigation to quantitatively and qualitatively increase the science that we actually receive. We ignored things, for the most part, like cost. We think this is very doable to the point of not really incurring a higher cost if we have an adequate sequencing infrastructure on board that can give us some basic logic and give us the ability to, say, dynamically build commands on the fly and what have you. Some open issues. Didn't really think through what kind of communication rates would be necessary to pull this off, but our feeling is that it'd be fairly low. You know, most likely hundreds of bits per second would be plenty in relay bandwidth to be able to coordinate these platforms together. You'd probably want kilobits per second or better anyway as a relay to the orbiter in order to get the data you're interested in off. And another open item really just has to do with the ruggedness of the platforms and their ability to survive for the conditions that are present in the Venus atmosphere and allow our sensors to continue to operate to a degree of fidelity to gather the information we need to do the profiling.
Clarification, you said kilobits per second for what?
For transmitting data between platforms so they can coordinate things like the altitude that they need to maintain to gather the information.
Okay, all right. Comments? Okay, so we're going to go on to this one where we have a chart. And which team owns this? The autonomous planetary flybys.
All right. Hello? Can everybody hear me? No.
It's on.
Test, 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 test. Okay, excellent. All right, so this is table 1 and 7 combined, and we were thinking about missions where you are trying to have a spacecraft observe an event of interest that's not necessarily there all the time, that could have a certain window where you need to observe it, or you might not know ahead of time where it is, and sending, mission after mission just to figure that out every time could get expensive. So how would we use autonomy to just do this in one go, perhaps? So what we thought about was that you could use autonomy to decide how to adjust your orbits as you're flying around to achieve better positions for these events of interests. If it's something that's on on a planetary body, you would maybe have a catalog ahead of time where you might check and again adjust based on that, just on what you're seeing. And then if you wanted to, for example, you're faced with a problem that you actually want to land something there and do some science, but you don't know ahead of time where that is, you could have perhaps have a mother spacecraft with some small sats or probes that you could kind of dispense onto these sites as you're observing them. But again, you would need autonomy to make the decision about what to send where. So you could do most of that data processing probably on the mothership, and then program your little helper probes that you can send out. You would, for example, create a landing sequence for the onboard child spacecraft. And also what you need to do, most likely, is update your onboard models locally as data is gathered, and you probably might not be able to rely on sending all of that data back and doing the processing then, so you might have to do that on board as well. And we were thinking this is, I guess we didn't put it down here, in the context of Europa and perhaps observing the plume, whether there's actually a plume there or not, but also it would apply to the heliophysics missions that we learned about earlier. And we have a second slide for this as well, so if we can go one slide more. Oh. There you go. So yeah, our motivators were that you might be uncertain about where the EOIs are located or about the environment ahead of time in general, unless you go through this process of sending mission after mission to kind of explore it ahead of time. So, but we were thinking about what can you do when you don't have that much a priori information. Also, there's a problem with the communication delays, right? So if you have to always send all that data back to be processed and for somebody to make a decision, that might be outside of the window where you can actually observe this event of interest. So in cases where that window is much smaller, you need autonomy to kind of figure out, okay, this is the action I have to take right now, because if I wait for somebody to tell me to make that decision later, I'll have missed it and will have missed the opportunity to do science. So the benefits of that is that you can do opportunistic science, and like we just said, is you can respond to the EOI when it occurs, and not later and have missed out. And maybe you don't even know that you missed something, right? Which would be a shame. And I think the challenges for that are, one is that you need to understand what to respond to and what sensors to put on the spacecraft in the first place to find those things, right? So there's a little bit of a trade here between like how much a priori information do you really need to know versus how much can you kind of gather from your sensors and find out when you're there and update your models when you're there. Really, I think if you have you need a lot of a priori information, that's going to cost you a lot. But then if you don't have a lot of information at a time, that might be a little bit more risky. But you have to make that trade. And then also understanding, making the decision of when to phone home and ask for a decision, because you have enough time to have somebody look over the data and make a decision for you, or when Autonomy says, no, I know that I don't have enough time to send all that data back and have somebody come back with a response. I need to act now. Making that, figuring out that decision, that's I think, also an open challenge.
Oh, it's over there. Sorry.
So did you guys talk about specific science examples where this would be beneficial? Like, do you have stories of where you've had missions that you wished you'd had this, or do you have something specific in mind?
Yes, we started from the Europa mission idea, but then we went to other types of mission. I mean, it could be earth science, or it can be heliophysics. But I think that planetary has the longest communication time. Since there has to be threads between the communication times back to Earth and the duration time of the event. So it really depends how you define the events.
Would you all like to use the magic box?
It seems like the difference here was opportunistic science, as opposed to we're going to go and measure something that we had planned to measure. This would open the possibility to find something of interest and then adjust the mission. Is that what you're saying? Okay. 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 Lunar Swirls? You got the box. Okay.
So, is it working? Hello?
It's working.
It is? Oh, okay. So Lunar Swirls, if you don't know what they are, there we go. They are strange features on the lunar surface. They are bright. They look like they are immature. And they don't have a topography at all. And what's most important about them is that they are always associated with magnetic anomalies on the moon. You can go to the next slide. So this is the near side and far side of the moon. And the next map, please. Shows you where the magnetic anomalies are located. There is a very large one on the, oh, okay, well, it's over. So there's a really large one on the, does it have a, on the, that's all right. In this area here, this is within a really, really large basin called South Polagan. It's the oldest basin on the moon. And within it are some volcanic features and lava flows, and including in one of them, located right here, I think, it's hard to tell, is a skylight or a vertical entrance to a lava tube, which is, of course, a great location to be having a lunar base. So it's also a great place to explore. I also said that they are immature. They look like they're fresh material, and this is because of these magnetic anomalies, that the magnetic anomalies and an electric field effect that is being generated as a consequence of that magnetic anomaly is actually blocking the solar wind from getting to the surface. So it is not creating some of the weathering products that we see, that what we call, how we know that the surface is older. There's also a really famous one right here. It's called Rainer Gamma. This is the most famous one. It was the first one ever seen. This is a big, big, huge volcanic patch of material, of basaltic material, and you can see the swirls really well here. Oh, I can go back, that's right. And that is this one right here. And then this one's on one of the far side ones. So these stretch several hundreds of kilometers across. And I think at this point I can actually hand it off.
So I'll talk more about the missions that we're envisioning for exploring these swirl regions and how autonomy can help make it happen. So we're thinking ambitious, so we are envisioning more of a mini campaign consisting of 3 phases. The first phase would be consisting of cheap CubeSats, a number of them that are in low lunar orbits, that can map out some of the magnetic fields and electric fields associated with the swirls. They would be doing distributed processing, distributed science goals. And at the end of their useful lifetime, we would like to crash them into areas of interest, L-cross style, and first of all, use that for up-close magnetic and electrical fields measurements, and also for analyzing the spectrum of the ejecta. The second phase would be more of a surface exploration, where we would like to send a hopper to one of the regions of interest. And the hopper can navigate rough and variable elevation terrain. It can do sample collection and analysis, so close to the surface we can do more precise magnetic and electrical field measurements. We can analyze some of the both fresh and mature material in tightly targeted areas. And that second phase would also serve as a technology demonstrator and technology maturation for the really ambitious third phase, where we would send a similar hopper to the far side of the moon, where it would operate in a fully autonomous fashion and explore the most interesting swirl regions. So in that third phase, we would conduct similar experiments as in the second phase, sample collection, analysis, up-close measurements of the magnetic and electrical fields. But it would need to navigate to cover significant regions fairly fast. So that's why we think autonomy is very important, and also because we won't be able to communicate with it as well as we could with the second phase hopper that's in more communicationally accessible regions of the moon. Did I miss something? Anything? Future? Oh, yeah, right. And we also see the first phase and the second phase especially as being beneficial to technology maturation cycles for autonomy, where we don't really care if, for example, some of our CubeSats fail. So we can take greater risks. We can attempt more ambitious science goals. And the same with the second phase hopper, where we're really building up to this more scientifically interesting third phase of the far side of the moon hopper. So even if we end the second phase mission prematurely, we still learn a lot, and we can hopefully mature our autonomy technologies enough to operate autonomously in the third phase. So that's our plan, and then we'll talk more about the technology maturation side of things and program side.
Right. So speaking from the perspective of a NASA headquarters technologist in planetary science, a mission like this is appealing from a number of aspects, because we understand that we need to build acceptance of the whole autonomous technology so that future missions can make benefit of it. And this, I think, as a mission concept, has an appeal from a number of standpoints. First of all, we're doing it with small sats, low-cost missions where we can afford to take risk and retire risk for future missions. As mentioned, we actually want, or don't mind, if you will, if we see failures. Because the second aspect that's appealing is we're doing this in cislunar space or near Earth space, where we can send the missions there, less expensively and more quickly. We don't have to wait a half a decade to get to our destination. We're 3 days away or a few days away. So we can send these missions, we can observe how they operate autonomously, and if they fail, we can observe the failure mechanisms and gain understanding so that we can retire the risk for future missions. And they're being done more cheaply. We understand that when we want to apply these technologies to future missions, we need to gain acceptance of the mission planners at headquarters. We need to gain acceptance of the users in the scientific community. We need to gain acceptance of the proposal evaluation community, TIMCO, if you're familiar with the acronym, who does the risk evaluation for our mission selections in planetary science. All of these groups need to be educated and accepting of autonomous technology, and so I think a concept like this has that appeal to it as well.
Okay, thanks. That was great. Question or? Okay.
So I can understand the appeal of the moon, and given the proximity and the ease, relative ease with which you can get to the destination, it could be a proving ground for more autonomous capabilities. But I was wondering, is there a particular advantage to going to the far side versus the near side of the moon for such a mission, especially when you're doing a surface asset? It's going to go to a very specific location, and maybe you can hop around. But there's a particular advantage, and if there isn't, then couldn't this be done through teleoperations from the Earth?
That's good.
Okay, so yeah, absolutely. So for one thing, we are actually talking about a near side first and then a far side. But the far side is just, it's more scientifically valuable. Everybody, at least every lunar scientist wants to go to the far side, wants to get that samples from the far side, because that is the oldest impact basin. It's also a really, really large impact basin. Actually, we're in competition with Mars for the largest basin in the solar system. I'm going to get probably a little bit too geology geeky here, but one of the big questions is whether that impact was actually differentiated, sort of like an entire magma ocean of the entire moon, whether that happened just on this kind of smaller but yet 2,500 kilometers across scale and several kilometers deep.
That's a separate science objective from these swirls.
That is true. Although at the far side swirls, we could actually be sampling fresh and mature material simultaneously. Without, we could literally have a lander land like right near a boundary, and be sampling these two things. Well, another thing I forgot to mention actually is the water or hydroxyl factor. One of the instruments, the Moon Mineralogy Mapper, was actually able to map hydroxyl across the lunar surface, and you can actually make a map of the relative abundance of, and I call it hydroxyl because it's a little ambiguous as to whether it's a water or a OH molecule only. At the lunar swirls, where those high albedo features are, they are depleted in hydroxyl and water compared to their surroundings, with the same sort of contrast as you see between the albedo difference. And in locations where it's a high albedo region to begin with, like in the highlands, and it's hard to see a lunar swirl, you can look at a hydroxyl map and then suddenly you can see it because it's all very depleted. So there actually could be this, there's this like phenomenon of like hydroxylization. This water's being created at the surface, and it's actually being differentiated by this magnetic/electric field effect. So, so that's why I'm saying at the far side swirl, it's scientifically just going to the lunar far side is a desired thing. But now we could also be going to a swirl, and we could be looking at the weathering, how the space weathering phenomenon. We could also be going to this one location where there's a known lava tube that we can access and check out.
But you still have to, so I'm wondering whether it's a driving case for autonomy, or it's autonomy, it's a proving ground for autonomy.
I would say that the far side is a driving case for autonomy.
You still need to communicate, so you need the system.
Well, if it was fully autonomous, we wouldn't need to communicate except to get the data back, right?
And another aspect of it is that, from what I understand, these features are fairly large, so hundreds of kilometers. So to be able to cover them effectively, we need to move fast as well, so which can be a challenge if you have to teleoperate and have a large team on the ground driving the rover or operating the hopper. And another thing I guess we didn't mention that is that this particular mission could also serve as a good precursor to human exploration of the moon and habitation of the moon, because these magnetic anomalies could be a good place to establish a base on, because there is a potential that they'll protect from some of the solar radiation. So, yep.
Okay, I think we need to, that was very good, thank you. We also have this all-sky stellar CME tracking, if I'm reading that correctly. Okay.
Oh, so we chose a new mission concept called All Sky Stellar CME Tracking. And what this would be is 15 or so CubeSat satellites. That number could go up depending on the signal-to-noise calculation, but they would be in a 3D array behind the moon or in a similar radio-quiet environment with about 10 degrees or so of 10 kilometers of separation between them. And what this would be like is portions of satellites looking in each direction in the sky, monitoring for associated type 3-like bursts for other stars. This is important because we've recently seen a couple of these for the type M dwarf stars, and they have big impacts into the potential habitability of planets around them. If they were having lots of extreme events that could preclude the formation of an atmosphere which is conducive to life. The autonomous aspect of this would be groups of spacecraft talking to each other and then letting the whole group know if they see a potential signal, and then they all synchronously point towards that potential signal, which lasts on the order of tens of minutes. And this would increase the probability of seeing interesting events, and you also could not do the whole sky with just one spacecraft with no autonomy. Autonomy kind of enables this whole sky monitoring system, and you also need to do active ranging with respect to some central node, because in radio interferometry, knowing the separation between the spacecraft is crucial. So you have to know that to some tolerance in order to do your post-data processing. That is about the gist of it. Are there any questions? Yeah, Jack?
I'm going to throw the cube.
So Alex, the idea, if I understood, was you've got this array of CubeSats, and each one initially looking at different areas on the sky. So here's the problem with the individual antennas looking at individual stars. Beam dilution, because your beam is really large, is going to make it very difficult to see sources, individual sources that will trigger. That's going to get swamped out by the background that you have. So you really need the power of the interferometer in order to limit your beam down to be able to even detect the burst to begin with. The good news is, though, such all-sky monitoring is being done, for example, at Owens Valley right now with the LWA array. So there are wide beam imaging that potentially you could do and accomplish potentially the same goal.
LWA is not truly all sky, since they're only seeing half the sky. But if you were to have, say, of 30 satellites, you have groups of 3 or 4 looking in each direction. they could narrow the beam in small groups. And once you know the area, then shift over the rest to tighten up that beam.
You're going to need more than one.
Yes, yes, yeah.
Okay, thanks very much. Is there a group? Okay.
So for our group, we also looked at Europa baseline mission. And I just want to point out areas that were not covered as we discussed the Europa lander mission. So we looked at 2 different mission phases where autonomy can be beneficial. One was during the landing phase. I think there was another group that mentioned. In addition to safe landing and navigation phase, also perhaps picking the best spot for landing. We didn't have any scientists in our team, but Europa, I guess, depending on where the geysers and plumes are, if there's an orbiter, perhaps orbiter can collect the data and have some decision-making process before actual landing. So again, use of autonomy in addition to safe navigation, also picking the right spot, correct spot for science collection. And the next phase, of course, would be during the science phase of the mission and where autonomy can be used. We looked at the 4 separate functions that can be used or is used during the science collection phase. Data acquisition, where the instruments are collecting the science data. Data processing function, where the data is processed. The decision-making phase is critical because, as it was discussed in other groups, how can we, especially with the limited mission, 20 days, how can we take advantage of picking the best location for drilling and sample collection? So part of this is then we looked at the required elements. One is the hardware, which I didn't hear in other groups, computing capability that is required for this mission. And we had Jeff Sheeha in our group that discussed a project that he's funding, at least actually it's STMD, SMD, and AFRL to address the performance and processor requirement. It's called High Performance Spaceflight Computing, right, Jeff? That is being funded by STMD, SMD, and AFRL, ARM-based multi-core processors, and rad-hard. So that's one element that we need, especially for these deep space missions where radiation environment is severe. So if we address the hardware side, certainly memory requirements, that's another element that needs to be addressed, high-volume memory banks. And then from a software, another element that I didn't hear much about being discussed is the assumption is we have a lot of data from the orbiter, for example, from the surface that we can use. And the type of software and algorithms that will be needed in situ decision-making. Certainly, if we can do a lot of that processing and training before the mission through use of analogs and any data that will be collected from the orbiter mission is useful. But is there any technology pool from machine learning and deep learning that can be used for in situ decision-making? I think that's an area that will be interesting to study. Other areas that were discussed, so the baseline mission, again, use of autonomy for decision-making. Since this is the lander, you're in one location, again, the decision-making process can be used, at least for the first half of the mission, to perhaps look at different locations that the arm can move to, traverse, and drill to maximize science collection, as was mentioned earlier. We also discussed other architectures, kind of out-of-the-box thinking. Since these missions are every 20, 30 years, one lander, one-time billion-dollar missions, how can we maximize or think out of the box for future architectures, perhaps multiple smaller landers that can land in multiple locations, because if you land in one location and you don't find life in one location, what does that mean? So looking at those kind of architectures that you can have smaller rovers, different instruments that can, again, the swarm topic that was discussed this morning, swarm of landers and rovers and different assets that can be deployed, collect different science data and communicate and work as a swarm, as a team, uplink the data to an orbiter and downlink to the ground. I think those are the type of architectures maybe in the long term that would be more beneficial, because just the limited opportunities for these missions, once every 20, 30 years, one spot, one lander. I think that's, and we had a lot of common other discussions with similar to other groups.
Okay.
All right,
So we don't have slides, and this should be fairly quick. The concept we looked at was really looking at Deep Space Gateway and how autonomy would influence science in that context. So with some of the expertise at our table, it was pointed out that currently the task loading of astronauts is fairly extreme and would limit the amount of time they would have to do any science work. So the thought is autonomy within the HEO system would benefit science, and at the same time we could leverage that autonomy for doing the science itself. So an example of that would be a habitat that has landed on a surface that is augmented by a set of rovers that could operate autonomously, doing surface sampling and so forth, and relaying data and actually perhaps taking sampling back to the habitat, where there would be a more robust autonomous system that could do analysis on that and provide input to either do further robotic studies or actually send astronauts out. So a couple of the things that I think this would require is really kind of a dual-use autonomous system, at least with the hardware itself, where it's both doing some of the management and maintenance of the hab itself while also having the ability to analyze science. So what that would really require is, we're seeing it as kind of a distributed autonomous system where you would have autonomy in the rovers itself and then autonomy in the hab. It would require things like, certainly robust surface comm. And perhaps the biggest challenge might be, integrating the SMD and the HEO people to get a unified system that could meet both sets of needs, both with the hab and the science analysis.
Randy, did you have any? Is Randy Lillard here? Okay.
So I'll pretend I'm both a HEO and science autonomy person. Two things to say about that. So raise your hand if you know that HAL exists for real. HAL. H-A-L.
9,000?
There is a system running on board ISS right now. It's called HAL. HAL stands for Higher Active Logic. It's built out of Draper Labs Timeliner software. It runs on the payload side of ISS. It is responsible for watching pieces of payload hardware that are turned on, and in particular, it's watching the power system. And it's designed to respond to problems inside the ISS power system. So on the one hand, we're kind of getting there. However, there's still some problems in demonstrating this, and this gets back to some of the things that Butler was talking about with respect to testing. So there was a demonstration of another piece of payload side automation on station that I conducted in 2015. We were told that we actually couldn't turn off parts of ISS and leave them off for too long if there were payloads inside the freezers inside express racks, because basically they didn't trust our automation. So that just reinforces the kind of thing Butler says about some of the problems that people have with us testing these systems. So I think you're right on, and I think it's a great idea, and we still have some work to do.
Okay. Any final comments? Did we get all the groups? Okay.
And I did have a slide. I don't know if I put it in the right folder. It's something group 16. Autonomous Workshop group 16. Anyway, my name is Ben Hockman. I'm in the Autonomous Systems Lab at Stanford University. And a good introduction would be this slide. Anyway, I'm just going to talk about a mission concept that I've been working on for the past 4 years as part of a NIAC project. And this is a collaboration with JPL, Isa Nesnis's group. And the whole goal of the project is to enable surface exploration of small bodies. So these are bodies that encompass asteroids, comets, small moons, anything small enough to be irregular in shape. And these have interest not only in the scientific community, but obviously in planetary defense, resource extraction. And so in some sense, it's the next frontier for a lot of exploration. There it is. So this is just a picture of our mission concept. And so this is a depiction of what we call our Hedgehog rover. So instead of using traditional mobility platforms like Curiosity, the microgravity environment of small bodies is such that you can't really get traction with wheels or anchoring devices. So we're extending the idea that a couple other space agencies have pioneered in terms of a hopper. So this is called Hedgehog because it has spikes on the outside, and its early conception looked like a hedgehog. But it operates on a pretty simple principle, and that's using existing hardware, namely reaction wheels, in a different sort of way. So by applying these internal torques to reaction wheels, this cube can hop and tumble across the surface. And it's robust in the sense that it's totally sealed from the environment, thermally and from dust. It can land in any orientation and be capable of hopping, so it doesn't need to self-right. And so when the outset of this project, I thought I was tackling a mobility problem, but it turns out that you need a high degree of autonomy to enable such a mobility system. So if we, for example, have objectives of visiting several different target sites on a small body, say Phobos. Phobos has been observed to have different spectral regions, blue and red, and we have a communication cadence that doesn't allow us to command every single hop that a rover takes. The microgravity environment can be such that hops take hours at a time. And so we need the ability to not command every direct hop. And so aside from the communication cadence, autonomy is also required in the sense that the dynamics on small bodies and the hopping trajectories that we might observe are very counterintuitive. So we can't even really inject a behavior that may be productive. For example, small bodies are often like irregular shapes, so like a potato. So the gravity environment on them can be very weird. They're often spinning at some non-negligible state, so the trajectories can be completely counterintuitive. So if you're trying to visit a specific location on the surface with a hopper, and moreover a hopper that can bounce somewhat randomly, you need the ability to learn some dynamic behaviors in simulation and build a model that can often be counterintuitive. And so we've developed some of the mobility system in terms of the control laws we use to get this thing to actually hop. And now a lot of our work is extending this into what the autonomy architecture might look like. And so on our study at Stanford, we're looking at the motion planning, but obviously this also involves localization. So how do you know where the rover is? So we've done a pretty broad trade analysis of what that might entail. If you can rely on a mothership with constant relay communication, it may be able to aid with localization. But there may be certain mission scenarios where you have large blackout periods. For example, if the mothership has an orbital pattern that doesn't allow it to always communicate. So we've been developing some onboard visual localization algorithms that allow it to, in some hopefully robust way, determine where it is. And then the motion planning problem. And that has to contend with these wonky dynamics and plan paths that may not always be intuitive. So even if you did have a very high communication cadence with the rover, you could use an intelligent planner to come up with control policies that might not always make sense at face value. So there's a lot of potential trade spaces in this mission type architecture, especially in terms of if you start to accommodate more than one rover. This has been always, we've been gearing this as a minimalistic platform so that it can be a secondary payload, low cost, so we can accommodate a little more risk. If you have some mass budget, though, there could be a trade-off between do you have more smaller platforms or fewer, larger, more capable platforms. Certainly there would be a different level of autonomy required if the rover needs to traverse away from a line-of-sight communication link with a mothercraft and it needs to report back, or if it needs to, like I said, operate and make decisions on where to take measurements without ground in the loop. So that's at a high level what this project has been focused on the autonomy side. Any time for questions?
Okay.
What sort of Earth analog can you simulate this on?
Yeah, you hit it the hardest question. So we test in different ways. We can test at a small scale what the dynamics of the actual hopping behavior is in certain test beds. We've got laboratory test beds that offload the weight of the rover. We've done parabolic flight campaigns where we can test at a local level how these flywheel mobility maps to these hopping trajectories. But of course, we can't really study the global nature of these weird trajectories in an Earth testbed. So we do rely heavily on simulation for the global studies of how you might navigate to distant locations. And the simulation is really the only environment that can capture these weird dynamics, the crazy stochastic bouncing nature, and as well as you use simulation because you can do it quickly. And when you have a highly stochastic system like this, you can start to, instead of understanding the deterministic nature of these hops, where you propagate your dynamics, how it stochastically behaves by Monte Carlo analysis. So to minimize risk, you might want to understand the corner cases of when a rover might bounce into a hole or into a bad situation. So simulations are really useful for doing many runs.
It's a really great mission, very interesting. I can see how you might learn some of the mass and gravity properties of the system during a bounce. I'm having a little bit of a harder time imagining how you can learn where you're going to end up, especially when I have very constrained resources in terms of total mission lifetime. So what if anything, have you thought about with respect to balancing mission lifetime with what you're going to learn?
Yeah, so a short answer to that is when we do the mobility analysis in these Monte Carlo simulations, we can start to get a sense of what the traversability of a certain region is. That is, in a probabilistic sense, how long does it take to go from one point to another? And so for a power-constrained rover, you certainly need to keep science objectives within the reachable space of your maybe few-day horizon. So what we do currently is we use simulations to do basically reinforcement learning to create control policies that say if the rover is at a certain location, how does it maximize its science reward under certain constraints? And those constraints can certainly include the lifetime of the total mission.
All right. Thanks very much. Appreciate it. We got everybody, I believe. Oh, sorry.
So we chose the Europa lander mission, and a lot of what we talked about was covered under Group 12, or I guess Group 14s, so we won't repeat that here. But we talked about what level of autonomy is required. There's task level, there's activity level, and there's goal-based level. And fundamentally, we believe that there has to be task level, and we think that there should be activity level autonomy. We talked about doing perhaps field demos early on in the project to build in some of the transparency that was discussed earlier this morning and get confidence and buy-in from the science community. But then we spent a lot of time talking about the difficulties of infusing technologies into a project even though it's only at pre-formulation stage. So that's hard in general, and it's specifically difficult for software. And how does one do that? That's a challenge. One of the things we thought about was perhaps we could infuse new technologies by when the instruments are solicited for the mission, that autonomy could be solicited for each one of those instruments as well. And so there'd be pieces of autonomous systems that would work together. Do you want anything? Questions?
Thanks, Carolyn. I think now we got everybody, correct? Okay, so